for us, variation of linked list like stack and queue. Okay, that is a linear linked list in workshop 1, right? Then in the second workshop, you learn non-linear data structures. For example, like trees and then also graph. Okay, and today we are going to look at not data structures. We are going to look at algorithms. Okay, remember there are two in the advanced level. We have two actually categories. One is on data structure and one on algorithms. And today in the third workshop, we are going to look at the algorithms part on searching. Okay, then in the next workshop, the last one, we are going to look at the sorting algorithms. Okay, so before we actually go into the searching algorithms, we are going to introduce to you what is algorithm analysis using big O notation here. Okay, because when you have different types of algorithm, sometimes we need to know, okay, which one is more suitable for us to use. Okay, so that's why we are going to look at this introduction to algorithm analysis first, using big O notation. Then after that, we are going to look at different searching methods. These are the three searching methods that we are going to see, like linear search, binary search, and then we will learn what is a hash table. Okay, because when you store your data in a hash table, the searching will become faster. Okay, then the last one, the last topic that we are going to see is one example for searching, a problem that you're searching, okay, to solve. Okay, so let's look at our first part, introduction to algorithm analysis with big O notation. Okay, so first we look at what is an algorithm, right? Okay, for example, okay, we look at a problem where, let's say, we need to cook an omelette. Okay, and these are an example of the step that we can follow. Okay, maybe you have your own different, step to cook omelette or to cook other things. But for this one, let's see. Okay, the first step is we try to get the frying pan first before we can actually cook. Then after we have the pan, then we try to get the oil, right? We need some oil to cook. Then, okay, when we try to get the oil, do we have oil? If we have, then we put in the pan. If we don't have, then what should we do? Then you have to decide. Do you want to buy? If you want, then you have to go out and buy. Or if you don't want, okay, I don't want to go out, then we can just terminate the whole algorithm. We don't cook anymore. Okay, if you don't have oil, right? So if you have solved this, let's say, okay, you have oil, you have the pan, then you put the oil in the pan, you solve this part already, then you go to the next step, which is, okay, now what should I do now? I'll turn on the stove. Okay, let's say after you turn on the stove, then the next step, or usually you pour the egg to the pan, right? And then you try to fry it and so on, right? Follow the step. Okay, I'm sure most of you have tried to cook omelette or even just some egg, okay, by yourself, right? Okay, so these are an example of a step-by-step procedure, but this one is to cook an omelette, right? But it's a step-by-step procedure, right? So algorithm is actually the step-by-step instruction how to solve a given problem, right? You must have the step, like you are given a problem that you need to solve, then you need to come up with the, how to say, we say the algorithm to solve this problem, which is actually the step-by-step instruction. How are you going to solve the problem, right? Okay, so, okay, so what is the most important properties in an algorithm? Okay, we have two properties here. The first one is correctness. The algorithm should be correct. This is very important, right? Correctness. Okay, for example, it should be able to process all your given input and provide the correct output. Whenever you input this, the correct output should be this, right? Okay, correctness is very important properties. The second one will be the efficiency of your algorithm. It's also very important. Okay, whereby your algorithm must be very efficient when you solve the problem. When you use it to solve the problem, for example, efficiency here we measure in terms of the memory and time it takes to execute the algorithm. We don't want to have an algorithm whereby you see, okay, even though your algorithm is correct, but it is not efficient. For example, or I need to run for 1 day, then only I can get the output. Then this is not an efficient algorithm, right? If possible, we try to make our algorithm to be, it can solve the problem as fast as possible. Okay, besides just being a correct algorithm, right? It must also be efficient as well. Okay, so these two properties are very important. For algorithms. Okay, when you design your own algorithms, you have to take into consideration these two properties. Okay, so for example, okay, let's say when you want to go from city A to city B, right? We have many ways to do this, right? How to travel from one place to another place. You can take flight if it's very far away, right? Or by bus, by train, and also by bicycle, or even if you want, you can walk also, right? But of course, it depends on the availability and also the convenience. Then you have to choose the method that is most suitable for you, right? So similarly, usually in computer science, you see, you will learn a lot of algorithms. For example, we talk about sorting. You want to sort something, right? There are actually many different sorting algorithms that are available for you to use to sort something, which you will learn in the next workshop, the last workshop, sorting. You learn different types. For example, insertion sort, selection sort, quick sort, and so on and so on. Okay, but which one is actually the best according to what you need? Okay, even though it's the same types of algorithm is for sorting, but sometimes we also have to know whether, remember, is the algorithm efficient or not according to your needs. Sometimes what you need, you want an algorithm that is very fast one. Then you have to analyze, okay, which of the sorting method here is the fastest one, for example, when I have this input. Okay, so that's why we need to learn how to analyze the algorithm. Okay, so here algorithm analysis can help you to determine, like just now what I mentioned, which algorithm is most efficient in terms of the time and the space consumed. Okay, so the goal of this algorithm analysis is we want to compare the algorithms, which is the solutions that you come up with to solve the problem, right? In terms of running time, but also in terms of other factors. Okay, like the memory that is used, maybe the effort, your line of code, and so on. Okay, so what is the running time analysis? So it is the process of determining how processing time increase as the size of the problem increase. Size of problem here is your input. Okay, so this input size is the number of elements in your input, and it depends on what problem that you are solving now. So the input can be of different types. For example, these are some of the common input types. Okay, like the size of the array, if what you are processing is an array, okay, or the polynomial degree, if it related to polynomial expression, number of elements in the matrix, okay, or the number of bits in binary representation, or if you are dealing with graph, then it might be your input can be the vertices and the edges in your graph. Okay, so these are some of the example of the input. So how do we compare algorithms? Like just now I told you that when, let's say, we have many different types of sorting algorithm, right? Or even let's say searching. Okay, now you want to find among all these algorithms that you can choose from. Okay, then how do you choose? Okay, how do we choose, right? We somehow we need to know how do we choose, right? Because if let's say I want something that is fast, when even though my input size increases, okay, so we need to choose which one is more efficient, right? So now let's look at how do we compare the algorithms. Okay, are we going to use the execution time to compare this algorithm that I can choose? Execution times here might not be a good choice because execution time sometimes is very specific to what type of computer that you are using. For example, a PC versus a supercomputer, okay, of course, if you use different machine, then the execution times of your algorithm can be different. Okay, so this might not be a good method to measure or to compare the algorithms, I would say. Okay, now the second method is, are we going to look at the number of statements executed? Okay, this is also might not be a very good measure because the number of statements, it actually varies with programming language, right? That you want to use, as well as the style of the programmer that write this algorithm. Okay. Okay, some people the code is very short, some people the code might be longer. So this might not be also a good measure, okay, to compare the algorithms. Now, okay, so what do we have any ideal solution? How, the method that we are going to use to compare the algorithms? Okay, so let's look at this. Okay, assume that we want to express the running time of our algorithm, right, as a function with respect to our input size and of the data that we are going to process. Let's say we call it as Fn. And we want to compare these different functions to the running times. So if we use this method to compare the algorithms, right, this comparison is actually independent of the machine time, and also like the programming style, whether your code is long or short, and so on. Okay, so that's why here, when we look at this algorithm analysis, we need to figure out how well the algorithm performs with respect to time and space, regardless of all the other inferences, right? So other inferences will be, or in other words, what we want is the environment within which the program runner must be fixed, okay? And we just try to analyze the running time that is not independent of the environment, okay? So our goal here is to compare the time and space complexity of different algorithms for a given input. And what is algorithmic complexity? Okay, it is actually defined as how fast your algorithm performs. Okay, where complexity here usually we use this Tn, which means the time versus the input time. The input size n of the data that you are going to process in. Using this algorithm. Okay, so and also here you need to take note that when we determine the complexity of the method or your algorithm, we don't really look at the exact number of operations that we are going to perform. In fact, we can ignore the exact number of operations. Like you say, this algorithm will perform 273 operations. We don't really look into this very detailed number of operations. Okay, instead we have to know the number of operations that is relates to the problem size. For example, let's say initially I just process let's say sorting. I use this sorting method number 1. When my data size is 10, only I need to just sort 10 elements in the array, or this is the time that it takes using this sorting method number 1. Now, if let's say what if now I increase my data size or the array size to 20, then how much time I need if I still use this sorting method number 1? Will it increase? Okay, or let's say now when my array that I want to sort the size now becomes 1000. So how much time it takes if I use this sorting method number 1? Definitely it will be longer compared to if your size is 10 or 20 or 30, right? Okay, here we want to know how the time actually increased when the problem size increase. You see? Okay, so for example, if your problem size doubles, does the number of operations stay the same, or the number of operations means the time taken, right? Or will it be double or increase in some way, like exponentially, for example? Okay, So this is what we want to find out when we compare the algorithms, right? Because you can have, let's say for sorting, many different types of sorting algorithm, or even for searching. For each of the searching method, we will also look at the big, how to compare it later, okay, when we look at the searching. Okay, so in order to compare the algorithms, right, then because what we want just now, as I mentioned, I just want to know when I increase my data size, will the time taken to actually run the algorithm still be the same, or how is it increased? So in order to do this, right, okay, we need a methodology to analyze the running time of the algorithm that will take into account the possible input, allow us to evaluate the efficiency of any two algorithms in a way that doesn't depend on the hardware and software environment. Like just now I told you, hardware can be, okay, when you run this algorithm in the PC, okay, it takes me, let's say, 5 minutes. But when you run in a supercomputer, wow, it's very fast, 1 second. Okay, then you can get your answer. So we don't want to evaluate, use a method that will be affected by the hardware. Okay, so and we can just perform this method by studying high-level description of the algorithm without actually implementing or running experiment to do the comparison. We don't have to do that. We just need to study the high-level description of the algorithm only, right? Okay. Now, let's look at one example to let you see what it means when you use different, different way to or different algorithm actually, okay, to solve the same problem. Then the time taken will be different. Okay. For example, let's look at this problem. It is a quite simple problem. Okay. So let's write a method that can help us to input an integer n. Okay. And then based on this n, we find the range of 1 to n. So for example, if my n is 10, what I'm trying to do here is I try to find out what is the sum of 1 plus 2 plus 3 plus 4 until plus 10. What is the total at the end, right? After I add up 1 to n. So how do I solve this problem? I think you should know already, right? How to solve. Okay, the easiest way is I will use this method. For example, okay, I will just use a for loop, right? And my for loop, I will start looping starting from 1 until n. And then inside the loop, what I do, just accumulate all the I value to a variable. Let's say call it as total sum here. And then at the end, just return the total sum, right? If you write this in the function, so then I will get my answer. Okay. So this solution is same as you scan out each can of soda separately in the supermarket. Okay. It means, let's say you buy 10 cans of soda or Coke, let's say any drinks, and then you go and pay. So when you go and pay, how the cashier help you to scan is, the cashier will take each of the can that you buy and scan one by one. So if you buy 10 cans, then the cashier has to scan for how many times? 10 times, right? If you buy 20 cans, then she has to scan 20 times. Or you buy 100 cans, then she scan 100 times. So you can imagine if you buy more, then the time taken for you to pay actually is longer, right? Because she scan one by one, according to how many cans you buy, right? Okay, so this is the same as this solution that we use to calculate the total sum. So how many times you actually execute this statement inside the for loop, or depends on how many times I loop, right? If my n is 10, then I will actually execute 10 times, right? Because I will loop 10 times. You see? If my n is 100, then I will execute 100 times, right? So if I use this method to solve this problem, then you can see that, this is if you talk about the operation, number of operations that you execute depends on the n, your data size, right? Okay. Now let's look at another solution that also can solve this problem, whereby I don't use any loop. I will use a formula. This formula will help you also to get the total from 1 to n by using this formula. So if now I use this formula to calculate the total sum, then you can see in my function now, I don't need any loop. I just put the formula here. Okay, just replace the n with the n that you pass in. So if my n is 10, then I just execute the formula. Just one line only, right? If my n is 100, also one line only. Just replace the n with the 100 only. If my n is 1000, it doesn't matter, also one line only. You see, no matter what is my n size, if I use this method to solve this problem or to calculate the total sum, I just need one statement only. Means the number of operations remains the same, no matter what is your n size. If I use this method to solve this problem, you see. So if we look back at our when you buy the can in the supermarket and pay, right? So this solution is the same as if the cashier, let's say you buy 10 can, how the cashier help you to scan is, she will just scan one can and then she multiply by 10. Then it's very fast, right? So no matter how many cans you buy, it doesn't matter, right? You buy 100 can also, she just scan one time and then multiply by 100. Okay, so that's why it's faster, right? If she do this, instead of scan one by one, okay, in the previous method. Okay, so this solution, the second solution is faster, right? It is faster because we use this formula. No matter what is my n size, the number of operations remain the same. It won't increase. But the previous one, this one is different. Depends on my n size, how many times I need to execute the operation, depends on the n size actually. You can say linearly, okay? Right? It's like your n, if your n is 10, then I execute 10 times. Your n is 100, I execute 100 times. But this one, it doesn't matter. No matter what is the n size, the number of here remain the same. It won't change. Okay, it's constant, right? So that's why you see when you try to find, you want your algorithm to be efficient, right? This second one will be much more efficient compared to the previous one. Okay, because this one doesn't depend on your n size, which is your data size. I'm talking about. Okay. So let's look at what is big O notation first, right? As I told you just now, now we are looking at algorithm analysis, right? And we are going to use this method called big O notation to help us to measure the algorithms. Okay, so that when you have the big O notation for this algorithm 1 and you have the big O notation for this algorithm 2, then based on the big O notation only, then we can know which algorithm is more efficient when the data size increase. Okay, so this big O notation is actually it's just a theoretical measure of the execution of your algorithm, usually in terms of the time, usually is in terms of the time needed, given your problem size n, which is the number of items. Okay, and the importance of this measure is it is useful when you try to decide whether your algorithm is it adequate enough, okay, for your requirement, or you need a better implementation. Okay, okay, or you find that, oh, okay, after the big O, you find that, oh, your algorithm will be very slow when your input increase. We have many different types of big O notation. Okay, later I will also explain to you what are the types that are available. Okay, so you see, okay, so big O notation will give you the upper bound. Upper bound here is the highest growth rate on the growth rate of your algorithm. So the growth rate here is the rate of cost of algorithm growth when your input size increase. Just like remember just now we want to calculate the total from 1 to n, right? So 1 to n, You see, when my n increase, how the algorithm grow, or how the number, the cost of algorithm can, is like the number of operation increase. Like just now, the first method, if I use the loop to calculate 1 to 10, right? So how many times I need to execute the statement really depends on my n, right? It grows linearly, actually. That is your growth rate. We say that grow linearly. The rate is linear. Okay, for example, right? But the second algorithm, it actually doesn't depend on the size. So the growth rate is constant one. It won't grow one. No matter what is your n size, it remains the same. Okay, so this big O notation will tell you when you have the big O, right? It will tell you how your algorithm will grow when your input size increase. Okay, in what rate? Okay, and it allowed you to ignore the constant factor and lower order terms and just focus on the main component that affect the growth of your algorithm. Okay, later you see how do we derive the big O, then you will see what I mean from here. The O here stands for order. The order here is referred to your growth rate of your function. It represents the running time that you need to solve the computational step. Okay, so for example, here, let's say you need to go to a shop to buy a car and also a bicycle, and you see your friend there, and your friend asks you, okay, what you buy? What you're buying here? Then you will say that, oh, I buy a car. Okay, why you say this? Because the cost of the car that you are going to buy is much more higher compared to the cost of the bicycle, right? Okay, so for example, if we look at the total cost that you need to pay, let's say when you buy car and bicycle, of course, you the exact price that you pay, you will add up together, right? But here, I mean, if you use big O, you just look at, you will just consider the cost of the car only, approximately. Okay, because the cost of bicycle, if you compare with the cost of car, is much more lower, right? So if we use big O, right, we don't really look at the lower order term, which is your cost of bicycle. You will just like look at most the cost of the car only, approximation. Okay, for example, if let's say the cost of the car and the bicycle we measure in terms of function. Let's say our function, this is our function n power 4 plus 2n power 2 plus 100n plus 500. So at the end, we will just look at the highest order term among all the terms here in your original function, which is n power 4. Okay, because n power 4 is the highest rate growth among all the other costs. So when we use big O, this is how we look at the highest rate. Okay, in all the terms that you have in your original Fn. Okay. Okay. So how do we use the big O to measure our algorithm, right? For example, okay, if you look at this graph, let's say I have two algorithms. One this pink color and also this blue color, right? So the big O for these two algorithms is given here. For the blue one, the big O is order of C, where C is a constant. And for this pink color one, the big O given is n power 2. Okay, so this n power 2, this C and n power 2, what actually it tells you? It tells you how the algorithm grows when your data size increase. You can n here represent your data size. Let's say if your data size is 1, only 2, 3, 4, and 5. And here the time taken to run the algorithm when your data size increase. Okay, so we can see that this blue color algorithm, the blue color one, you see the big O is order of C, right? So you can see that no matter what is your n size, the time taken to run is only 5 seconds. It doesn't increase one, it remains the same. This is similar to the way how we calculate 1 to n using the formula, right? No matter what is the n, I just need this formula to calculate, that's it. Okay, but the second one, this pink color algorithm, big is n power 2. N power 2 here means when your data size increase, the rate or that this algorithm will increase in terms of time is n power 2 rate. So you can see that when your n is 1, that you see the time taken is very little, right? Okay, it's actually less than 5. But when your n become 2, you see that it increased to almost 5. When your n becomes 3, it's 9, power 2, right? 4 is 16, then 5, 25. Okay, so you can see that when you increase a bit of your n, the time taken will increase also quite fast. So how fast? It depends on what is your big O notation. If it's n power 2, then it increase in the rate of n power 2. Okay, it can be n power 3, it can be n also. Like our the total of 1 to n, the first method, it will increase of in terms of order of n. Okay, so based on the big O that you can derive from the algorithm, right? Okay, so let's say now you have 3 different algorithms that you can choose to use to solve the same problem. So you want to know when you want to analyze these 3 algorithms, right? Because you want to know which one is more efficient when my data size increase. We don't want to have an algorithm where, okay, when your data size only 10 or everything run very fast and everything very okay. But when your data size increase to a bit only, then you see that, wow, how come it takes much more longer to get the output? We don't want this, right? So that's why you need to analyze your algorithm. Okay, and the big O is actually like provide you a method by using big O notation to analyze it so that you know when your data size increase, right, will your algorithm will become slower. How slow? If it becomes slower, then you need to know how slow. Is it in terms of just linearly like n, or is it n power 2? Of course, n is better than n power 2. The best one will be is C, constant. It doesn't depend on your n. So this is what we try to find out when we use the big O notation. It will tell us this kind of information. Okay. Now, and also when we look at when we analyze the algorithm, right? We also need to know which input the algorithm will take less time and which input the algorithm will take longest time. There are actually 3 types of cases that you can analyze when we analyze the algorithm. Okay, the first one is we can analyze in terms of best case scenario. So best case scenario will be if your data is arranged in a way when you run the algorithms, it needs to examine the fewest data item. For example, best case scenario will be, let's say when you try to search for an item in an array that is not sorted. I should say, if you want to find okay, you are searching for an item, okay, in an array, okay, in an array. So what is your best case? Your best case is, because how to search for item in array, usually you need to compare each one, right, until you find out, right? So your best case will be the first item that you compare is what you are searching for. Okay, that is your best case scenario. Worst case scenario will be your data is arranged in a way when you run the algorithm, it needs to examine almost all the data, or you examine you do the maximum step. Okay, so for example, if you use back the same example, what you are searching in the array is the last element, or it doesn't exist. So if it doesn't exist, what you how much step you have done? You have to compare all the element already in your array, right? Then only you find out that, oh, it actually doesn't exist, but you have done the maximum step already to find everything. Okay, an average case will be with random ordering of the data. You run the algorithm where it can land in best, worst, or in between the cases. Then you just run many times the algorithm and try to find out the average case. Okay, so average is somewhere between your best case and your worst case. Okay, so when we measure the algorithm, sometime we will look at, okay, if I have the best case scenario, what is my big O? If I have the worst case scenario, what is my big O? And also the average case, what is my big O? Okay. Okay. So let's look at how do we derive the big O? But before we can derive the big O, right? I just want to let you know, when you have, let's say, your code, and you try to find out what is your the function, okay, the fn, and then from the fn, remember, like just now we have n power 4 plus n power 3 plus 100n and then plus 500, that one. So you have to come up with that one, and then from there we can derive the big O notation. Okay, so how do we come up with this fn based on your code that you write? Okay, let's look at if you have consecutive statement in your code. Okay, the time complexity for this consecutive statement is you just add up the sum of individual time complexity. For example, if you have equal, right, this will take one step. J plus plus, okay, increment operation is also one. This one, J slash equals 2 is actually J equals to J divide 2, right? This one will take 2 steps. One step for the equal and one step for the division. So that's why 2. So if you have these 3 statements in your code, this will be calculated as 1 plus 1 plus 2, so 4. So this 4 here, okay, for best case, average case, and worst case, it is also 4. Still remember just now I just tell you what is best, worst, and average. Because in these 3 statements, do we really have a best, average, and worst? We don't really, because no matter how, we have to execute these 3 statements, right? So your best, worst, and average will be the same. So that's why it's 4. Okay. Now, what if, let's say in your code, you have a loop, either a while loop or for loop, right? Okay. Average and worst case time complexity are the same. So let's look at how do we calculate the time step for your this loop. Let's look at a very simple for loop. So in this for loop, we have j equal to 0, then j less than n, j plus plus, and inside the for loop, we just execute this statement, k equals to k multiplied j. So we first we look at the header of the for loop, how many operations we need to execute. So for the for loop, you can see from here, j equal to 0, definitely this one you need to execute, right? This will require one step, right? Equal, remember? Okay, not equal, this is assignment operation. Then j less than n, when you compare less than n, it's also one operation, right? And then j plus plus. Sorry, this one should be from here, and n plus 1 should be here. Let me adjust a bit. Yes. Okay, it should be here. Okay, so that you don't confuse. Okay, so this j equal to 0, it require one step, right? Because assignment. And then j less than n. Okay, to compare j less than n, this one will require one step. But why n plus 1? Because how many times you need to execute this part here when you look, right? How many times you need to execute? Depends on how many times you look, right? Because every time, this is the condition part. Whether do you still need to actually execute the for loop? It depends on this part, right? Okay. So it's n plus 1 time. And then this j plus plus, you need to execute n time. Assume that, let's say this for loop, you look from j equal to 0 until n minus 1, right? Because your condition is less than n. So you need to execute from 0 to n minus 1, which means you need to execute how many times? N times, right? Okay, because you start from 0. So n times, it means that this j plus plus, every time I loop, I need to increase one time, right? So this part I will execute n times, right? Because I loop n times this for loop. And then why this one is n plus 1 time? Because every time I look, I also will check again what is my j. so that whether my condition is still true, so do I still need to look, right? It's n plus 1 because for the last time when your j equals to n, you still need to compare, right? You need to compare and then to determine that, oh, it's false, then only you terminate the for loop, right? That's why it's n plus 1 time. Okay. And okay, so this is our header. Our header, the number of operation is 1 plus n plus 1 plus n. You add up these three together. And then for the statement inside the for loop, okay, it's only k multiplied equals to j, right? So this we require 2 steps, but because we execute n times, so the total number of steps will be 2 multiplied by n is 2n inside the loop. Okay. So then for the total time step that you need is you just add up the header operation in the header together with the number of operation inside the for loop. It will be 2n plus 1 plus n plus 1 plus n. So total will be 2 plus 4n. So if you want to know how many time steps, you just depends on the n. If your n is 10, you just replace this with 10, then you know. Okay, so you come up with your the time complexity for this for loop here. Okay. Okay, if you have a nested for loop, if you have nested for loop, you just if based on our just the previous for loop, you can just use the same concept to calculate. For example, if this is our code here, before the for loop, we have this assignment operation, total equals 0. So this one only require 1 step, right? Because assignment. And for this outer for loop here, we also start from j equals 0, j less than n, j plus plus, similar to our previous for loop. So this one step, assignment, comparison will be n plus 1, right? And then j plus plus is n, okay? Because this for loop will loop n times, right? And then inside the for loop, now inside this for loop is more complicated compared to the previous one because here we have another for loop. But for this statement, before the inner for loop, total equals to total plus j, this will require 2 steps, right? And then for this inner for loop, is also from k until n minus 1, it also loop n times. Then the statement inside is total equals to total plus k. So we know that this one here, it will require 2 plus 4n because this inner for loop is similar to this for loop that we have seen, right? Okay, it's also 0, j equal to 0 until less than n, right? And the statement inside is also similar. Okay, just that here is plus, and here we use k only. So this part here, it will require us 2 plus 4n, like the previous one here, right? Okay, so then we know that, okay, how many times this, okay, so we know we add up the total operation inside this for loop here, it will be 2 plus 2 plus 4n, right? And then this outer for loop, it will loop n times. So that's why here we multiply it by n, the whole thing. Okay, n multiplied by 2 plus 2 plus 4n. So you just add up everything together. So at the end, you get 4n power 2 plus 6n plus 3. And here you can see that when you have 2 for loop nested, your time complexity usually is n power 2 because it's nested. But the previous one, you only have 1 for loop, right? You can see your time complexity is only n. Okay. So where n is how many times you loop, right? You can say that it's like your data size. Same also for this one. Okay, so this is how we calculate for nested. Then for conditional if else statement, okay, how do we calculate for if else, right? So if else, you see, if else means selection. It's like, if this is true, I execute this. If this is not true, then I execute this. You select which one you want to execute, right? So based on this one here, the condition in my if is j modulus 2 equal to 0. So this part here, whenever I want to check whether this is true or not, I need to perform 2 operations. J modulus 2 is 1 operation. This equal to check whether it's equal to 0 or not is 1 operation. That's why 2 operations in this header for my if. Okay, if this is true, then I execute this statement, which is j equals to j divided 2, then this one will require 2 operations. Else, I will execute this part here where I will put j equals to 1 plus j multiply j divided 2. How many operations? Assignment 1 plus 1, multiplication 1, division 1. So 4 operations. So how to calculate my time complexity for this one? So for if else, your worst case and average case will be different. For example, what is worst case? Remember, the worst case definition is you need to execute the maximum number of operations, right? If based on my this if else statement, the maximum will be when you encounter the else part, right? Because else part, it takes you 4 operations. It's like the true and the false, I should say. If you encounter the true part, you execute this one, it requires 2. If you execute the false part, it requires 4, right? So 2 plus 2 is only 4. 2 plus 4 is 6. So your worst case scenario is 2 plus 4. Okay, which will be 6. Okay, your best case, actually best case is 2 plus 2, and you encounter the true statement. 2 plus 2 only 4. How about average? Average, okay, if we know what is the probability of getting true and false, okay, assume that here the probability of getting the true and false is 0.5, same. So my average case, I can calculate 2 plus p true, the probability of true here is 0.5 multiplied by 2. This 2 here comes from here, the statement for the true, the true statement. And then the 4 is the statement for the false statement, right? So that's why 2 plus p true multiplied by 2, then 1 minus p true, which is 0.5 as well, based on our here, multiplied by 4. Then you get around 5. Okay, this is one way. How can we calculate this if else statement, conditional statement? Okay, and for recursion, okay, let's see. Okay, how about recursion? How do we actually calculate the time complexity for recursion, right? You have learned recursion in also the previous workshop, right? Okay, where you need to call the same function again inside the function, right? So it will keep calling and calling and calling. So let's look at this factorial recursion function. So when I want to execute this recursion, you see, okay, go inside, I will check out if my n more than 0, I will call the function again, pass in n minus 1, multiply n, right? Else I just return 1, my base case, and this is my recursive case. Okay, so how to determine the time complexity for this recursion function? So this part here, when I go inside the function, definitely I have to check if my n more than 0 or not, right? So comparison, this will require me 1 step, right? 1 step. And then if this is true, then I will call the factorial n minus 1 multiplied by n, right? Okay, I don't know how many times I need to call because it really depends on my n. Okay, so that's why here I just put tn minus 1 first. How many times I need to call? Then plus 2. The 2 come from here, n minus 1, you need 1 operation, and multiply, you need 1 operation. So plus 2. And return, we don't count any operation. That's why it's 0. Okay, so the else part is 0. So, okay, now we need to determine what is this tn minus 1. So then only I can come up with my time complexity, right? And then based on the factorial formula, I know that, okay, if my n is 0, when I pass into the factorial, the time complexity is only 1. Why? Because based on the formula, the recursion function here, if the n that I pass in is 0, then I compare. I must compare here, right? 0, so I want call function, I return 1. So I need to execute this part only 1 operation because the return doesn't count any. Okay, so that's why here tn is 1 only if your n is 0. But if your n is more than 0, it will be 3 plus tn minus 1. This one come from where? 3 plus tn minus 1. It actually come from here. If my n is more than 0, so I will go inside the function, I still need to compare here. It requires one step, right? And then I will call the function again, right? Because my n more than 0. So that's why it's 1 plus this tn minus 1 plus 2. So it's 3 plus tn minus 1. Now we just have to figure out what is this tn minus 1. Okay, so in order to know what is this tn minus 1, we can use the knowledge of the sequences and the series to sum. Okay, where this 3 plus tn minus 1, we know that, okay, we can 3 plus, we can expand this part here, 3 plus tn minus 2. Then we accumulate all the 3 out, like 3 plus tn minus 2. So equals to 3, we put a 2 here, means 2, 3, okay, plus tn minus 2. So this tn minus 2, we can expand it further, 3 plus tn minus 3, then we take out the 3 here, so 3 tn minus 3, right? Because this, why we keep n minus 2, n minus 3, because here, remember, whenever you call the function again, you need to minus the n by 1, right? If not, you will have infinite loop, right? Your n doesn't change in the recursive function. So we have to minus the n, and you just keep continue until when you n minus n, right? Somehow you will reach the recursive case where your n is 0, when you n minus n. So from here, when you come to here, you have accumulated how many? 3n. You have 3n, okay? Or n times of 3 lah, okay? So then finally you get 3n plus 1. So this is your time complexity for this factorial function. Recursive, using recursive to recursion, okay? So this is how you can calculate the time complexity for a recursive function. Now, let's look at, okay, you come up with your time complexity, right? Then how do we derive the big O? Like for example, you have this, how do I derive the big O for this, let's say, recursive function? How do I know what is the big O? How, let's say I want to know how the times that it takes when your n increase, when I run this factorial function, right? So I need to derive the big O, because the big O will tell me how it grows, okay, when my n increase, right? So there are 2 steps that you can use. The first step is, for each of the term in your Fn, right, you set the coefficient term to 1. Okay, it's like you can remove all the coefficient you don't need. Then the second step, just keep the largest term among all the terms that you have, and the other just remove it. Okay, let's look at one example. Let's say my Fn is this one. N power 4 plus 2, n power 2 plus 100n plus 500. First step, remove all coefficient, right? The coefficient here is like 2, 100, okay, 500, all this remove. So you're left with n power 4 plus n power 2 plus n. And then remove all the smaller factors. So when you compare this n power 4 plus n power 2 plus n, smaller factor will be n power 2 and n. The largest one is n power 4. So you keep the largest one only, n power 4, and your big O will be order of n power 4 for this Fn. Okay, so it means that this algorithm, how it increase, the rate that it increase based on your data size is n power 4, you know. So it means when you increase n a bit, the time taken will be increased a lot. Okay, this is not efficient, this algorithm, if you have this. Okay, now similarly, okay, let's look at a few more examples. If you get this Fn, right, 7n power 4 plus 3n power 3. First step, remove all the coefficient. You have n power 4 plus n3. Second step, keep the largest one. So n power 4, so you get, the big O that you write is O n power 4. Okay, if this is your algorithm, the Fn that you get, 4n multiply log 2n plus log 2n, you remove all the coefficients, so you remove the 4. So you're left with these 2 terms, and then keep the largest one. Largest one will be n log 2n instead of log 2n only. So your big O will be order of n multiplied by log 2n. Okay, how about if you get something like this? You don't have n. Your formula, or your Fn is 7 plus C only, where C is a constant value. Okay, it's not your data size, it's constant one. Okay, then step 1, remove all the coefficient, you remove 7, you're left with C. And then step 2, you also of course remain C only. But when you write your big O, you don't put order of C, you put order of 1. So whenever if your algorithm at the end, your big O is order of 1, this is very good. Means your algorithm is very fast. It means you don't have any n, right? You don't depend on the n. Means your data size. It's just like just now we use the formula to calculate the total of 1 to n. No matter what is your n, I just need this formula to calculate that's it. Okay, the number of operation remain the same no matter how your n increase. Okay, so this is how we write order 1. Okay, so why we just keep the most significant term, like just now I just keep n power 4. I don't want those n power 2, n power 3. I don't want. Okay, because in general we don't want to bother with this non-significant detail, because the big O, remember just now, it's just a conceptual thinking. It's just a concept, okay, that tell you roughly approximation how your algorithm the rate will increase when your data size increase, right? We don't really look at the it will increase 97 operation. We don't want to talk about until so detailed. We want to know in general. Okay, when I increase my data size, how my algorithm will increase. You see, not algorithm, the rate or the time taken, how it will increase to run it. Okay, so that's why we use big O notation to represent the most significant terms. Okay, for example, if you get order of 4, like just now the C, you change it to order of 1. We put order of 1, means it's constant. If you get order of 4n, you put n only, like you don't put 4n power 2, you just put n power 2. Okay, because order of n power 2 is always more complex than your Cn, if your C is a constant. For example, n power 2 is larger than compared to, I don't know how many 0 here, multiplied by n, right? Because n can be infinity also. Okay, so here 18. Okay, so 10 power 18 will be insignificant if you have, your n is infinity. That means infinity multiply power 2 definitely is bigger than this. Okay, so if you use the same thinking, then if you have this complexity, you don't put 4n power 2. We don't look at the 4. We just look at the n power 2. Okay, since if your n is infinity, it doesn't matter what you have for 4 or you have for 10,000 or whatever thousand, it's not significant. Okay, if you compare to your n. Okay, so now let's look at you know how to derive the big O. So when you have the time complexity for this algorithm, then you can derive the big O. So what are the types of big O that you can have, and what does it mean? Okay, so if your big O is order of 1, means constant, you don't depend on any n, right? So the complexity here is constant. Okay, let's say here in this table, the n size we are talking about is 10,000. Let's say the data that you want to process is 10,000, right? So if your big O is constant, order of 1 operation, of course, we consider it as 1. It's very fast, microsecond, okay, to process or to run the algorithm. If what you get is log 2n, then you just log 2 with 10,000, you should get around 14. Okay, this is logarithmic. Your complexity is logarithmic. It's also quite fast. Okay, if you have order of n, then number of operation, of course, is 10,000, right? It's linear type. Okay, then it's around 0.1 second. Then you also can have linear logarithm n multiplied by log 2n. So it's around 140,000. So the time is also 15 seconds. Quadratic n power 2 is 10,000 power 2, you know, the number of operation is quite a lot, right? It takes around minutes. Okay. But if you have polynomial n power k, then it's 10,000 k. It will take hours. Wow. And then for the last two, exponential and factorial. Can you imagine how long it takes? order of C power n, if you have exponential, your n is the power you know. Then you have 2 power 10,000. It's quite larger. It's intractable. I mean, it means that the time it takes will be very long for the last two. Okay, intractable. Okay, or the worst one is factorial, n power factorial, 10,000 factorial. Can you imagine? It's a lot. Okay, so it's intractable. So you can see that these are all the big O that you can derive, you know. Okay, and then what it means, okay. So here from here, you have some idea that if the big O I get is n power k, this is not good. It means when your data size increase a bit, the time it takes will be very long to execute the algorithm. Then you will know that this algorithm is not efficient. So you might want to change another algorithm. Okay, or you might want to change your algorithm so that you can get one that is more efficient, which is smaller than this polynomial. At least you get quadratic is better than this polynomial, or linear logarithmic, okay, and so on. So you try to change your algorithm, okay, because you don't want it to become slow, right? So let's look at if you have order of 1, I mean it means what is the scenario that you're having? If your algorithm, if the big O that you get is order of 1, usually it means your algorithm is independent of the size of your data in which it operates. For example, array element access, random access, right? Means when you access array, no matter which element in which position, the time it takes to access is the same. Unlike linked list, remember in the workshop 1, we look at linked list. How do we access any elements in the linked list? You always have to start from the first node, right? And go to the second one, go to the third one until you reach the one that you want. So if you want to reach the one at the last, then it depends on how many elements you have in your array. If you have 10, then you need to look 10 times, right? But if you access the first node, then it's only 1 time. I mean, you don't need to look at all. So that's why for element access in linked list, it's not order of 1. It's actually, you can say order of n, worst case scenario. Okay, depends on the data size, on the element, how many nodes you have in your linked list. But for array, it's different, it's random. Okay, you can, because for array, when you access the element, you basically calculate the address, I would say. So that's why you can access any element with the same number of time. Okay, order of 1 doesn't depend on data size. If you have order of n, your algorithm performance is directly proportional to the size of the data set being processed. For example, when you want to print the content of array or your linked list. Because this one, how do we print the content in array or linked list? Remember, you need to go through every element, right, in your array or in your linked list. So you need a loop, right? You need a loop. So how many times you loop depends on how many elements you have in your array or linked list. That's why if you have one loop, usually it's order of n. Remember just now, how do we calculate the loop? The final fn that you get, usually you will have an n there. So it means it depends on your data size. It's like it increases linearly, like the time taken based on your data size. Okay. Okay, you can also have order of n plus m. This is similar to order of n, but just that maybe in your algorithm, you need 2 data sets. That's why it's n plus m, where maybe your n and m, these 2 data sets are of different size. But their combined size determines the performance. Okay. Then you can have order of n power 2. N power 2, usually you have 2 nested loops. Remember just now when we calculate the time complexity for the nested loop, the time complexity that you get at the end usually is n power 2. So it's like usually when you have a nested loop, you will get n power 2. Okay. And for n power 3, n power 3 means you have 3 nested loops. Okay, usually it means you have 3 nested loops. You will come up with n power 3 at the end. Right. If you have n power 4, You will have 4 nested loop usually. Okay. This log2n, okay, how can we have this big O for log2n? Okay, you have learned binary search tree, right, in your second workshop when you learn tree, right? Okay, so when you search in a binary search tree, okay, because how do you search? You start from the root, you check, okay, is this the value that you're searching? If not, then you determine, right, because for your binary search tree, you have left, right. So you determine either do I have to go to left to search or right to search? Depends on what you want to search. Is it bigger than the one that you're comparing? If it's smaller, then you should go left. If it's bigger, then you should go right. So you choose one path to search only in your binary search tree. That's why every time you are going to like, or either go left or right, you choose one. So that's why it's like you divide it to 2. So it's log2n. Okay, for this search in a binary search tree. You can also have n log2n. Okay, this algorithm will deal with a set that you partition iteratively. Okay, where, okay, you will see this big O notation n log2n when you in our next workshop, the fourth one, when you look at sorting for merge sort and quick sort, then you will understand what it means by n log2n. Okay, because when we sort, okay, we also divide it into 2 parts, and then you sort each of the part separately, and then divide again and sort, divide again and sort. Okay, so that's why it's log2n is for the division of your array to 2 parts, and then the n is the sorting process for each one. So it's n log2n. Okay, for this merge sort and quick sort example. Okay, how about order of 2 power n? This one very slow, right? 2 power n. So this algorithm is exponential time behavior. Your timer and space will double every time you add a new element, and until it become intractable. Okay, so this example is like when you try to place 2 power n pieces of rice on a checkerboard. Let's say you have this checkerboard, right? It's 8 times 8, right? Yeah, 8 times 8. So you want to place, okay, the first one, place 1. Then this one is 2 power 0, 2 power 1, 2, 2, 3, 4, 5, and so on. So your 64 is 2 power 64. Okay. So if the algorithm that you get, your big O is this one. At the end, I mean, when you look at it, it's order of 2 power n, then you need to consider to change your algorithm, okay, to a more efficient one. If you have this n factorial also, is even worse than this. Okay, so you have to consider to change your algorithm. Okay. Okay, I think now it's 9:43. Okay, I think we will stop here because you have the second session coming up, right? So we will continue again around 11. So in our second session for the advanced workshop, I'm going to let you see 2 types of searching, and the hash table is a way how do we store the data so that our searching will become faster. Okay, and after that we will look at what I mean an example for searching. Okay, so let me stop my sharing first. I think you can go back to your main room there. Okay, for the second session, it's a guest speaker. Okay, I will see you again around 11.